It's kind of wild to think about, but the exact same physics that governs a devastating car crash is also responsible for a brilliant game-saving catch in a cricket match. Welcome to This Explainer. Today, we're diving into the invisible math that dictates, well, pretty much every collision, catch, and explosion in our universe. We're talking about momentum, impulse, and the math of motion.
So here is our physics playground for today. We'll quickly define momentum, look at the conservation principle, and actually solve some collision problems together. After that, we'll get into explosions, rockets, impulse, and force, and finally wrap up with how all this math applies to sports and impacts. Let's get right into it.
Starting right off with our foundation, defining momentum.
So every moving object carries something with it, right? It's this kind of physical oomph that makes it hard to stop. And the math behind it is actually incredibly simple. Momentum, which we represent with the letter P for some reason, is just mass multiplied by velocity. That's literally it. P equals m times v. It's the product of how heavy something is and how fast it's going. And since we measure mass in kilograms and velocity in meters per second, our unit for momentum is exactly what you'd expect, the kilogram meter per second.
To really put this into perspective, look at how these two variables balance each other out perfectly. Say you have a light, 2 kilogram mass, but it's moving fast at 10 meters per second. That gives you a momentum of 20 kilogram meters per second. But on the other hand, if you take a heavier 5 kilogram mass moving way slower at just 4 meters per second, you know what? That also gives you exactly 20 kilogram meters per second. A light, fast object packs the exact same mathematical punch as a heavy, slow one.
Now, let's move on to the conservation principle, where we look at unchanging totals.
Momentum gets really interesting, honestly practically magical, when bodies actually interact. The absolute crucial rule here is the principle of conservation of momentum. It states that when bodies interact, the total momentum remains completely constant, as long as no external forces act on them. So if we can ignore external forces like friction, the total momentum right before a crash is perfectly equal to the total momentum right after. It's like an infallible cosmic accounting system.
And the best part? We can prove this in the lab with raw data. Imagine we roll trolleys down a slightly tilted runway, just tilted enough to cancel out friction. We use photo gates to track their speeds super precisely. When a moving trolley slams into a stationary one, and they stick together with Velcro, the raw data consistently shows this. The total mass times velocity before the collision perfectly matches the combined mass times the new velocity after.
All right, let's actually solve a collision problem together. The 90 kilogram crash.
Let's treat this like a puzzle we need to solve. What happens when a 60 kilogram truck traveling at 3 meters per second collides with and joins a stationary 30 kilogram truck? What is the common velocity of these two trucks after they crash and stick together?
Okay, let's just walk through the math step by step. Step 1. What's our total momentum before the crash? Well, the moving truck is 60 times 3, which is 180. The stationary truck is 30 times 0, which is 0. So our starting total is 180. Step 2, momentum after. They stuck together, right? So we add their masses. 60 plus 30 is 90 kilograms. We multiply that by our unknown velocity, v, giving us 90v. Step 3, because momentum is perfectly conserved, we literally just set them equal to each other. 90v equals 180.
Divide both sides by 90, and boom, 2 meters per second. That combined 90 kilogram mass moves off in exactly 2 meters per second. The math is just so elegant, and it proves the rule perfectly every single time.
Next up, explosions and rockets, which is basically momentum in reverse.
So let's completely flip the script, because this exact same conservation math applies to things blowing apart. Remember, momentum is a vector. It cares about direction just as much as magnitude. If a stationary object suddenly explodes and splits apart, its starting momentum was 0, and because momentum must be conserved, the total momentum after it splits still has to be 0. That means the forward momentum of any flying pieces absolutely has to equal the backward momentum of the other pieces, perfectly canceling each other out.
This perfectly explains recoil. If a rifle fires a bullet forward with a momentum of, say, 3 kilogram meters per second, the rifle has to kick backward with exactly 3 kilogram meters per second. So if the rifle weighs 6 kilograms, we just do the math. 6 times v equals 3, meaning the rifle recoils backward at 0.5 meters per second. And honestly, it's the exact same principle for a deflating balloon or even a space rocket. Firing a high-velocity stream of gas backward creates an equal and opposite forward kick. That's literally how jet engines work.
Moving right along into impulse and force.
This is all about manipulating time.
So how do we use force and time to actually mess with momentum? It all comes down to this massive equation. Impulse equals force times the change in time, which also equals the change in momentum. Basically, a resultant force is simply the change in momentum per unit of time. And believe it or not, this is actually just another version of Newton's second law hiding in plain sight. It tells us that to change an object's momentum, you have to apply a force over a specific amount of time.
Let's try another numerical puzzle to see how this impulse equation applies to a real life or death scenario, like a car crash. Imagine a 1,000 kilogram car traveling at 24 meters per second. It crashes and comes to a complete rest in just 1.2 seconds. What is the steady stopping force applied to that car?
All right, let's figure it out. First, what is the total change in momentum? The car was at 1,000 kilograms times 24 meters per second, which is 24,000. It came to rest, meaning its final momentum is 0. So the total change is simply 24,000 kilogram meters per second. Next, we use our equation. Force equals the change in momentum divided by the time it took. So we just divide 24,000 by 1.2 seconds.
And the result? A massive 20,000 newtons. That is a staggering amount of force required to rapidly decelerate a heavy vehicle like that. And it's exactly this immense force that causes major damage, which perfectly sets up our final section on safety in sports.
Finally, sports, impact, and math, the real-world applications. Let's take all this impact time physics and apply it to the real world. Think about a batter following through with her swing. By doing this, she's increasing the time the bat is in contact with the ball, which increases the impulse, resulting in a much larger momentum gain and a much faster hit. But now contrast that with a fielder catching a fast-moving ball. Notice how he draws his hands backwards? Why do that? Well, he wants to purposefully extend the stopping time. A longer time means a drastically smaller average force on his hands, taking all that painful sting right out of the catch. And this brilliant application of extending impact time is literally everywhere. It's exactly why cars are engineered with crumple zones. They intentionally crush to prolong the collision time and reduce the deadly force of an impact. It's why your seatbelt is extensible and stretches slightly when you jerk it. It's even why long jumpers land in deep sand pits instead of hard dirt. The sand yields, extending the stopping time, which applies a much smaller stopping force to their bodies. By manipulating time, math quite literally saves lives.
Which brings us to our final provocative challenge for you. If you hit a 30-gram stationary billiard ball for exactly 0.001 seconds with 50 newtons of force, based on our Impulse Toolkit, how could you use math to increase that ball's final velocity? Would you swing harder to increase the force, or would you follow through to increase the time of contact? I'll leave you to experiment with those variables in the real world. Thanks for joining me on this explainer, and keep looking out for the incredible math in motion all around you.